All right, welcome to part 3 of our polynomials notes. So here we're going to talk a little bit about division, and you can see here we have some terminology to review. You can see we have the dividend, that is the expression or term or number that we are dividing. The number doing the dividing is the divisor. The result of that division is a quotient, and if a quotient does not divide evenly, it will have a remainder. We know that an improper fraction is when our numerator is greater than our denominator. This is all new, old information here. We know that if we were to divide, the result would be basically the product of the divisor and the quotient, and any remainder would be added. You can see here that each of these pieces correspond to one of the definitions we've quickly discussed. And then finally, let's use this one for the divisor. We know fundamentally that division and multiplication are related. When we divide, we write the dividend in divisor in descending powers and making sure we insert any placeholder zeros with any coefficients. So I'm going to demonstrate this first example kind of step by step, and then I'll let you guys try the next one on your own. So here we are going to divide x to the third minus 1 by x minus 1. So when we write this, our dividend will go in as x to the third plus 0x squared plus 0x minus 1. Notice I included those two placeholder zeros just to ensure that I'm dividing properly. So now we're going to go through this long division process. It's the same process that we would perform if we were doing long division, way back when in elementary school. We ask ourselves, how many times does x go into x to the third? Well, it goes in x squared times. Notice that I'm lining up my variables, right? I have x squared here in the same column as that 0x squared. Once I have that x squared, I multiply. So I multiply x squared times x and get x to the third. And then I multiply x times negative 1 to get negative x squared. The next step here is to subtract. X cubed minus x cubed is 0. 0x squared minus negative x squared is positive 1x squared. We bring the next term down and then go through that same process again. Again, we're going to ask ourselves, x goes into x squared how many times? Well, that goes in x times. We then multiply the x times x and get x squared. X times negative 1 is negative x. Don't forget, we are subtracting at this step. We will get 0, and we will get 0 minus a negative. Well, that's going to be positive x. We bring the next term down and go through the same process again. We can see that that's going to happen nice and clean. X goes into x positive 1 times. We multiply and get x minus 1. When we subtract, we get a remainder of 0. What we have on the top of our long division bar here is the quotient. That is the result of our long division. So I would like you all to pause here for a minute and try the example you see on your screen now. All right, let's see how we did. You can see here my work. You'll notice a few things on the setup here. We were missing a term, right? In our original dividend, we had 3 terms for a cubic. Just a quick note here, we should always have one more term than the highest degree polynomial, highest degree term in our polynomial. So I included that placeholder 0x squared with my setup. Other than that, the process is pretty similar. When I got to the end, I had a remainder of negative 156, and we will write that remainder as you see here in blue. We will rewrite it as a numerator dividing by our divisor, x plus 4, that divisor coming from the original problem. Now that's a long process. That's not why they call it long division, but it can feel like that. We can also divide using what we call synthetic division. It's really a shortcut, and we can use this when our our divisor, has a lead coefficient of 1. Divisor is in the form x minus a, where our lead coefficient is 1. So in this case, we have a divisor of x plus 3. So we would take -3 and put it in a little half box. We would then list out our coefficients as we would on long division, including any missing values. Oh, I don't need that positive sign there. And I can see here that I have 1, 2, 3, 4, 5 with a 4th degree polynomial. I've accounted for all my missing terms. How did I know that the 0 goes here? Well, my exponents 4, 2, 1, and 0 are already accounted for. We were missing the coefficient between x to the 4th and -10x squared. So that's the setup for synthetic division. And then we will draw this horizontal line, and we will bring down our first term. From here, things speed up. We will multiply -3 times +1 and get -3 as a result. We will then add the next column, and then we're going to do the same thing. We're going to multiply -3 times -3 to get +9. We add, we multiply, we add, we multiply, and we add. Our last term underneath the the synthetic division symbol is our remainder, and these remaining quantities are the coefficients on our resulting quotient. This has 1, 2, 3, 4 terms, so it must be cubic. So we would write our final answer as x to the 3rd minus 3x squared minus x plus 1 divided by x plus 3. This shortcut, this synthetic division, is also helpful in evaluating polynomials. It is a shortcut for evaluating a function at a specific x value. So here we can see that we are trying to evaluate f of -4. So I'm going to plug that value into my synthetic division box and then list out my coefficients. I'm going to follow the exact same process I just did on the previous problem as if I were synthetically dividing. So the first term would get carried down, and then we multiply and add and multiply and add and multiply. And when we finally add here, we get -93. That's all we need to do. This value here, our remainder, is the value of the function when x equals 4. In other words, f of -4 is -93. I think that's a much faster approach to evaluating polynomials, right? Especially as we get more and more comfortable with this synthetic division process. All right, so the last bit of this, we are going to return to that rational root theorem and take a look at a graph and see how we can use that to help us solve these polynomial functions. Now, we know from our quadratics work and from our practice even with linear stuff going back to Algebra 1 and Algebra 2, that x-intercepts can be thought of as solutions to these equations. Solving an equation like we see here, g of x, seems pretty tricky. We can't use a lot of the algebra skills we've developed over time. We have to find another way. So what we can do is we can use a graph to find a real rational x-intercept. So here I have this graph, and I'm trying to find my x-intercepts. I can see that I have one at -2, but these other x-intercepts do not occur at nice, easy locations. Our goal is to find these solutions in fully simplified radical form, so we have to follow a different process. So I know that the value of the function here when x equals -2 is 0. What this allows me to do, it allows me to kind of chop down my my polynomial into a more manageable form. Now, also notice here, this is a double root. You can notice that the x-intercept at that specific point, our graph touches and then basically bounces, right? It doesn't cross through the x-axis. So what I'm going to do is this is an application of that rational root theorem that says, well, if -2 is a solution, I can divide out that root and keep working. I have a missing linear term here, so I need to include that 0 in that fourth spot. But I know my remainder here is going to be -2. 3 times -2 is -6. We add to get 7. We multiply to get -14. We multiply again. We add, we multiply, and as expected, we have 0 as a remainder. So that's helpful, but what we also know is that that was a double root, so we can do this same thing again. We can divide by the resulting polynomial, ignoring our remainder, and we can go through this whole same process again. Again, I'm going to get a remainder of 0. I know that I have that double root from my graph. So again, the 3 comes down, and we multiply and add and multiply and add, and I multiply, and again, I find that I have 0 as a remainder. What all this means is that I can rewrite this mess of a polynomial that we had nothing to do with as x plus 2 times x plus 2. There's our double root that we saw in our graph, right? Trying to color coordinate them, times the resulting polynomial of all that synthetic division. 3x squared plus x minus 1. Now, while that polynomial is not super easy to deal with, excuse me, let me rephrase that. What we've done is we've rewritten a fourth degree polynomial as a linear times a quadratic. Why that helps us? Well, we have all these different ways to deal with quadratic functions. We can use a quadratic formula, we can factor, we can do a lot. So I will have 3 unique solutions here. I'll have x equals -2 with a multiplicity of 2. And then my other 2 solutions will be, well, they'll come from our quadratic formula. -1 plus or minus the square root of 1 squared, minus 4 times 3 times -1, so that's plus 12, all over 2 times 3, which is 6. Fully simplified here, our other 2 solutions will be -1 plus or minus the square root of 13 over 6. So the idea of the rational root theorem is that it allows us to break down a messy polynomial into more workable parts. We can do this either through guessing and checking or by graphing and finding an x-intercept. If you're up for it, I'd like you guys to try the next example, example 2. We're attempting to find all the zeros possible. I'm going to do this without a calculator. If that's how you'd like to try it, I'm going to go ahead and pause and work this out. All right, so here's how I worked through this. You can see that I did this without a calculator. I identified through the rational root theorem all the possible zeros. Again, those are related to the last term and the first term, all the possible factors of those quantities. So I started guessing and checking. There's nothing special about -1, but as I synthetically divided, I found that it had a remainder, therefore it is not a root. My next guess was at -3, and what I found is that did have a remainder of 0. What that means is we can rewrite this polynomial x cubed plus 7x squared plus 11x minus 3 as x plus 3 times x squared plus 4x minus 1. We've chopped it down to size in a way that's more manageable. That linear factor is easy to solve as x equals -3. The quadratic one, a little bit more complicated, but it's just the use of the quadratic formula. I find that I have two non-rational roots, -2 plus or minus root 5. All right, we've almost made it here. The last bit we want to do is we will see questions where we need to create a polynomial from its roots. So good thing to note here, imaginary roots occur in conjugate pairs. So what this means is that we are going to write a polynomial of quadratic factors if it's a fourth degree polynomial. Well, if I have roots of 2 and -2, I know that that would come from x squared minus 4. I could also think about that as x plus 2 times x minus 2, but because I want to write this as quadratic factors, I'm going to use x squared plus 4. Now that I is a little strange. I need to figure out how I can create a quadratic that has a solution of I. So I like to do this process of solving for 0, where I will say, well, x equals I, well, really equals plus or minus I because it always comes in a conjugate pair. Well, where did that come from? Well, I know that imaginary numbers come from square roots. So if I got plus or minus I as a result, I would have taken the square root of -1. So if I square both sides, I have x squared equals -1. I solve for 0, and my other factor here will be x squared plus 1. So we've met most of the criteria here. We have a product of quadratic factors, which will lead us to a fourth degree polynomial. The last bit we need to account for here is f of 3 should equal -150. So what we do is we say, well, there's going to be some multiplier outside. This multiplier will not change our, it will not change our zeros. And we're going to plug in -150 for y, and we are going to plug in 3 for x. So in this case, I'll have 9 minus 4, and then I'll have 9 plus 1. That means that -150, that point they gave us, is going to be a times 5 times 10. So our a value, when it's all said and done, will be -3. Our perfect answer here would be y equals -3 times x squared minus 4 times x squared plus 1. I'd like you guys to go ahead and try the last problem here. It's been quite an experience getting through all these polynomial notes. There's a lot of information here. We are going to attempt to solve this. If you'd like, you can try to do it without a calculator and try to guess at those rational roots. That's how I will demonstrate it. You can go ahead and pause here and take a look in just a minute how I solved it. All right, let's wrap this up. So what you can see here is because of the relatively highly factorable number 24, we have a whole lot of possible roots here. I'll be honest, there was a little bit more guessing and checking than what you see on the page right now. But what I ended up with is after some guessing and checking, I found that +2 was a good root in that it got me a remainder of 0. And then even at that point, through some investigation, I can see that it's going to be difficult to factor that resulting polynomial by grouping. So unfortunately, we need to go through that whole same process again. Now 12 doesn't have quite as many factors as 24, but there is still quite a few. And once we go through with the rational root theorem and find a good root, we find that again 2 works. So all of this is to say that 2 is a double root, and the result of that second level of division led us to a quadratic times a double root. The double root gets us our solution with multiplicity of 2, and this quadratic we solve through the formula, and we find that we have an imaginary set of solutions, a pair of solutions. Nice work, guys. Way to hang in there. There's a lot of information here, and you made it. Nice job.